Hello, in this tutorial I'm going to show you how to model a cantilever beam with a beam element model. Um, this is the cantilever beam. It's 1 meter long. It's going to take a point load of 100 newtons at the right hand end, and it's a 42.4 times 3 millimeter round tube section made from standard steel. And we can see the results that have been generated from SkySieve, which is a Euler Bernoulli based calculation program, and we can see that the tip deflection is 2.3 millimeters, and there's a maximum stress, bending stress of around 29 megapascals. So I'm going to switch to ANSYS. I'm going to use the static structural system. And the first thing I'm going to do just before I start, I'm just going to open up the engineering data, double clicking it, and I'm just going to check that I've got the same values. In fact, the only thing that's different, although it won't make really any difference here, is that the Poisson's ratio in SkySieve is a little different, so I'm just going to change that, but the Young's modulus is the same. That's the main thing, so I can close that. I'm now going to model. I'm going to use Design Modeler, so I'm going to right click. The default is Space Claim. I'm not going to use that. So I'm going to click on Design Modeler. We have to wait a second while it opens. Okay, I'm going to work so that my beam length is in the X direction. So I'm actually going to look at the XY plane, and I'm going to look at that plane. I'm then going to draw a curve, which is going to be a straight line. I'm going to come through, click on line. Actually, before I do that, I'm going to change the units to millimeters, and I'm going to click on the middle here, and then I'm going to make sure it's horizontal and just click anywhere. I'm then going to dimension that, use the general dimension tool, and that dimension is going to be 1000 millimeters per meter. I can just zoom to see everything. If I go back to the model now, I should see that I have a sketch. Now there's a few ways that I can turn this sketch and the curve within this sketch into a line, which is the ANSYS Workbench terminology for a model that can be then meshed with beam elements. So the way I'm going to do it is I'm going to come up to concept, and I'm actually going to use the lines from points. I find this works pretty well. I'm then going to click on the two ends of my line, pressing the control button so I get both of them. Line turns green. Let's press apply, and then I'm going to press generate. What I should see is a tick appearing, and then I have one part and body, and I have a line body. I'm only going to be able to generate mesh on objects, well, parts and bodies that are within this little drop-down menu here. Then click on the line body. I come down here, I always look for where there's yellow because that means I need to do something, and I can see I need a cross section. So to generate a cross section on here, I come to the concept again. Down the bottom there's cross section. I click circular tube. I need to put in the radiuses of this, and I can either do this on the CAD screen over here, but I'm just going to enter them in directly here. So the outer radius is 21.2. and the inner radius is 18.2. That gives me a wall thickness of 3 millimeters, and that's all I need to do. I can now come back to my line body, and where it says cross section, I get a drop down menu, click on circular tube. That's now complete. I can leave that open, or I can close this window if I want. I'll just leave it open. I'll come back to the workbench home screen, and I'll double click on the model. Wait again a few moments. And it opens up. I'm using ANSYS 2020 here, which is the same version that you can download from ANSYS in well, this is July 2020, so this is what's available at the moment. Oh, did I click on the right thing? Here it is. Okay, so what I've got is, here's my line. The geometry is read in. There's lots of ticks there, which is good, which means I can come here. I'm just going to do the very basics. I'm not going to play with the mesh. I'm just going to generate a default mesh. And what I see is that it looks kind of like a tube, but of course these are beam elements. The way I can make sure that I'm understanding what I'm actually seeing is come to the display menu and untick the thick shells and beams. This is the actual finite element model. These are the elements, okay, but ANSYS likes to can actually visualize the actual construction of the cross section. But I'm going to leave it as a beam actually because it's easier to deal with, because then I'm going to put a fixed support on my left hand end like that, and I'm going to put a force on my right hand end. I'm going to make that force, I'm going to describe it by components so I can make sure I work in the, I'm always going to apply force in the Y direction. That's going to be my vertical. It's minus 100 because I want it to act downwards, and the geometry has just got to be applied, so it's actually applying it at the end. Once I've done that, I can solve it, and the thing I'm going to just compare just for now, just for this very simple example, I'm just going to see the directional deformation, and I'm going to look at that in the y-axis. That gives me my vertical deflection, and I'm going to solve. Now wait a moment for it to solve, and I hope everything turns green. I tick on my Z axis there so I can see it in XY coordinates, and then I click on my directional deformation and I can see it deformed. And actually I might just put the units into millimeters so that I can see I've got a deflection of 2.31 millimeters. If I go back to my result, I can see that my Euler-Bernoulli value is 2.3, just under millimeters. So we're very close to our results. So we're verifying very simply this this cantilever beam model. And that's where I'm going to leave this tutorial. Obviously, the exercise is to now continue looking at verifying and maybe even validating this model. And obviously, I'm going to record 2 further tutorials showing you how you model the same beam, but with shell elements and with solid elements. Okay, thank you.